homework time. Happy homework time is here again. And so let's jump right in. Start by writing our name at the top of the paper. Here's the dealio. I'll write my name. You write yours. Likewise, I'll write the date where and when I am, because it's always today. And you write the actual date where and when you are, month, day, and year. Great. Well, from all that we've been doing in multiplication division, now suddenly veer off in this side path, and we're going to be looking at factors and multiples, prime and composite, which actually ties in very closely. This is perfect timing for it because we've done multiplication, we're starting division, and now we're going to say, okay, how does all this prime, composite, factors, and multiples, how does this relate to multiplication and division? So accordingly, our instructions are to record the factors of the given numbers as multiplication sentences and as a list in order from least to greatest. Then we will classify each number as either prime with capital P or composite with capital C. Whew, we don't have to write out those long words every time. The first problem is done for you, and when we look at it, we find something, a rarity here in Eureka Math land. 8, they're telling us, is equal to 1 times 4, which we know it's not. I do this kind of thing all the time. We won't give our Eureka friends a hard time about it. We all do this, but really it should be 1 times 8 is 8, and 2 times 4 is 8. And so when you look at the factors, 1, 8, 2, 4, those are the numbers which can be multiplied in some configuration and give you a product of 8. And so we'll put them in order from, as it says, least to greatest, 1, 2, 4, 8, separated by commas, and that is composite because it has more factors than just one in itself. And just so you understand this whole thing of listing factors with the commas and everything, prime and composite, this is not just a Eureka Math thing. This is a math thing. So this is the way everybody does it. Okay, so when we look at the next one that we are to do, with the number 10, always start off, just good practice, start off with 1 and times the number itself, because that's a given. Any and every number in all of numberdom has 1 in itself as factors. Okay, so 1 times 10 is 10. And now, what else can we multiply? What other factors can we multiply and get a product of 10? Yes, 2 times 5 is correct. Yes, 2 times 5 is 10. Is there anything else? 3 times something, 4 times something? No, okay, so there we are. Okay, and we don't have to use a commutative property and write these all twice, switching the order of the factors. So for what we have for factors are 1, 10, 2, 5. Put those in order from least to greatest. So 1, 2, 5, 10. Now, is it prime or composite? Well, it's greater than 1, and it has factors other than 1 in itself. It has 2 and 5 as well. So that there is a composite number. It's composed of more factors than just 1 in itself. And so now with 11, let's start off as we did, as we want to be our want, and say, well, 1 times itself, 1 times 11, indeed is 11. And you probably know just by looking at it, but hey, 2 times anything, 3 times anything, 4, 5, 6, no, there's nothing else, no other factors, pair of factors I can multiply and get 11 as a product. So the factors of 11 are 1 and 11, which are easy to put in order, aren't they? Now, that's the very definition of prime. It's greater than 1, and its only factors are 1 in itself. So that is prime. And just like with Optimus Prime from Transformers, right? Prime means first. So these are the first numbers, so to speak. These are the prime numbers. I don't know, go figure it out. Prime the pump, why don't you? So 14, we'll say 1 times 14 is a good place to start. Equals 14. What else can we multiply? What other factors can we multiply and get a product of 14? Yes, 2 times 7. And now stop and think before you leap away. Are there any others? Anything else we can multiply and get 14? 3, 4, 5, 6, 7. Nope, nothing else. And notice I stop at 7. There's a reason for that. Because anything greater than that midpoint surely cannot be multiplied by a whole number and get the number that it's doubled. Does that make sense? It really does. All right, so our factors are 1, 14, 2, 7. But we'll put them in order. 1, 2, 7, 14. And it has more factors than just one in itself. So indeed, yes, this is another composite number. All right, well, let's jump on, and there's more to be done here. Let's go. And look, there's lots more to do, so let's just jump right in, shall we? Yes, we shall. Okay, so we're always going to start off with 1 in itself, so we don't forget to do that. So 1 times 17, we'll start off with 17 equals 17. Is there anything else? 2 times anything? 3, 4, 5, 6, 7, 8, 9 even? No. So those are our only factors of 17. The only numbers we can multiply and get a product of 17. So our two numbers are 1 and 17. Okay, fits the definition for prime, doesn't it? Yes, indeed. So that's a prime number. Only factors it's greater than 1. Only factors are 1 in itself. So let's look now at 20. So we start off with 1 and 20. Always a good place to start there. Equals 20. And we want to make sure we don't miss any here because we know right off we've got more coming. So let's go ahead and go in order. 2 times something? Yes. 2 times 10 is also 20. 3 times anything? 4? Ah, yes, that's right. 4 times 5 is 20, yes. Remember, we only have to go to the midpoint. We don't have to go through every number because, as I was saying, there's not, like, you can't take 16 and multiply it by a whole number and get 20, like, or anything after that midpoint. So 6 times anything make 20, 7, 8, 9, we already got 10. Okay, so the factors of 20 then are 1, 20, 2, 10, 4, 5, which we will put in numerical order. 1, 2, then 4, 5, 10, and don't forget what? Yes, that's right, 20 as well is one of the factors. And now that's obviously, yes, composite because it's composed of more factors than just one in itself. Let's try 22. We'll go ahead and do 1 times 22 to start with. And now let's just kind of go through the numbers up to the midpoint. 2 times anything? Oh, yes. How about that? 2 times 11 is 22, right? 3, 4, 5, 6, 7, 8, 9, 10. We have 11. Okay, well, that's it then. So 1, 22, 2, and 11. We will put in order from least to greatest. 1, 2, 11, 22. So obviously that is, yes, composite. It's composed of more factors than just one in itself. Let's try 23. We'll go ahead and write 1 times 23 to start off with. Is 23. What else can we do there? What other factors can we multiply to get a product of 23? 2 times something? 3? No, 4, 5, 6, 7, 8, 10, 11, 12. No. That's it. That's it. So the factors of 23 are simply 1 and 23. And that fits the very definition of prime, right? It's greater than 1, its only factors are 1 and itself. And when we look at 25, we know what we're looking at, don't we? We'll start off as we always do here with 1 times the number itself. 1 times 25 is 25. 2, 3, 4, well, we know, okay. All right, everybody's jumping right to 5 times 5. Yes, of course. 5 times 5 is 25. Make sure we don't miss anything, though. 6, 7, 8, 9, 10, 11, 12, there. Okay, yep, that's it. So now this is the first time we've encountered this. When you have 5 times 5, as in this case, or any number times itself gives you that product, you do not list it twice as a factor. You just list it once. So it would be 1, 5, 25. Those are the factors. I'm not going to say 1, 5, and 5 because 5 is 5, isn't it? So 1, 5, 25. And this will actually happen with all the squares, which is a whole nother topic. But, you know, and 2 times 2, 3 times 3, 4 times 4, 5 times 5 as we have here, 6 times 6 is 36. All of those will be written in this manner. So is that prime or composite? Okay, yeah, because it has more than just 1 in itself as factors there. We have that 5 as well. It's definitely composite. Good. All right, with 1 times 26, we'll start off with 1 times 26, yes, for 26. And you can see, you know that it's evenly divisible by 2. Why? Because it's an even number. There we go. So 2 times what? There you go. 2 times 13 is 26. And when you go through the rest of the numbers up to the midpoint, like 3, 4, 5, 6, 7, and what I'm doing when I'm saying these numbers, like, is there anything I can multiply by 7? That'll give me 26. Well, no, I know 4 times 7 is 28. You see, I really know your multiplication facts to do this easily. 8. And if you don't, by the way, if you're still working on your multiplication facts, that's fine. You should have a multiplication table in front of you. And so when you're going through, you actually have something to look at. Otherwise, I'm just counting for you, and that's kind of useless. So as we go through, we find that that's it. So 1, 26, 2, 13. Put them in order from least to greatest. 1, 2, 13, 26. So obviously that is, yes, composite. It's more factors than just 1 in itself. Now with 27, let's do 1 times 27 is 27. Anything else? Can we multiply 2? No, because it's not even. 3? Oh, yes, that's right. Good thing you know your math facts there. Yes, 3 times 9 is 27, isn't it? And is there anything else? Kind of go through the numbers yourself. Nope, that's it. So 1, 3, 9, 27. We have for factors of 27, 1, 3, 9, 27. So that clearly is composed of more factors than just 1 itself. It is composite. And lastly, for this set here, we'll start with 1 times 28 is 28. And we know right off, hey, this is an even number, so we know it's going to be 2 times something. So 2 times what? Yes, 14 is 28. Is there anything else? Well, look, 14 goes into that number, and 14 I could write as 2 times 7, which suggests to me very strongly that 7 is probably a factor of 28, isn't it? Oh, it is. That's right. Yes. Now 3 isn't, but 4 is, because 4 times 7 is 28. See how I did that little trick there? You like that, huh? Yeah. Go tell your neighbors. All right, 5, 6, 7. Go through the rest mentally. Okay, there's nothing else there. So I have 1, 28, 2, 14, 4, 7. Put them in order from least to greatest. So 1, 2, then 4, 7. What comes next? 14, 28. And so that is clearly very composite. In fact, you notice something here, look. 1, you can make a rainbow if I were to draw the lines, which I'm not going to. But 1 times 28, 2 times 14, 4 times 7. You see how the factors end up arranged in that way? All right, wow, well, all of that was just number 1. Yeah, let's go on to number 2. And here in number 2, our instructions are to find all factors. We just did that. We know how to do that for the following numbers and classify each number as prime or composite. Explain your classification of each as prime or composite. So factor pairs for 19. Well, this is what I said. Always start off with 1 in itself. So 1 and 19 are the factor pairs. To start with, anything else? You going through the numbers with me in your head? Yeah, that's it. Yeah, so this is prime 19, and you see I'm going to explain my classification, is prime because its only factors are 1 and itself. And by the way, note that its is the possessive its, which does not take an apostrophe like the contraction for it is. So anyway, factor pairs for 21. Well, we'll start off again with 1 in the number, 121. Didn't we just do this? No, maybe we didn't. Okay, so what else can we multiply to get 21? Yep, you got it. 3 and 7. Good, you know that. And that's all, right? So 21 has more than just 1 in itself. So 21 is composite because it has more than 1 and itself as factors. Now, if this seems like a lot of useless writing, you're wrong. Because this is the kind of thing that I tell you, as a teacher, if I read your sentence here and it says something like this, I say, good. She understands it. She's got it. She understands the difference between prime and composite. But if I read this sentence and then that cues me in as well, like, okay, I need to work with her on prime and composite. So factor pairs for 24. 1 and 24 we'll start with. Number itself and 1. It's an even number, so we know it's evenly divisible by 2, right? So 2 and 12. Now think for a minute. 12 is 3 times 4, isn't it? That suggests, rather strongly, that 3 and 4 are also going to be factors of 24, because I could write 2 times 12 as 2 times 3 times 4, couldn't I? Yes. So let's check out 3. 3 times what is 24? Ah, yes, 8. And 4 we said as well. 4 times what is 24? 6, yes. And then all that remains between these, you see how we kind of go on down and up there, is 5, which is not a factor of 24. And we already did 6. We can think 7, 8, 9, 10, 11. There's 12, and nothing after the midpoint will be. So those are all of our factor pairs. So obviously this is not prime, right? It is composite. So 24 is composite. Because it has more than 1 and itself as factors. And they gave you this one to show you that, hey, look, if it even has just one more factor pair, it's composite. Even if it has a bunch of factor pairs, it's composite. The only thing that makes it prime is when it's just 1 in itself. All right, so there's number 2. Hey, there's only 4 examples to do tonight, so let's go check out number 3. Well, in number 3, we meet a little friend named Brian. Sorry, but Brian is a punk, yo. Check it out. Brian, just kidding. That's not nice. Brian says that only even numbers are composite. Only even numbers are composite, Brian says. So in other words, he's saying also that all odd numbers are prime. And now the reason we're given this about Brian, who doesn't actually exist, is because this is a common misconception, is that we're saying, oh, okay, so even numbers are composite, odd numbers are prime. Now there is something of a connection between even, odd, prime, composite, but it's not a straightforward this is that. Otherwise we would not need the words prime and composite. They describe something different than even and odd, although there is a connection there. So let's find out what that connection is. So if we list all of the odd numbers less than 20 in numerical order, I guess they want to know that we can count. So just the odd numbers, though. Okay, odd numbers less than 20 in numerical order. So 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. Okay, so now 1 is special, very special, just like you. So 1 is special. It is neither prime nor composite. Is 1 prime? No. Is it composite? No. It's a unit. It is neither prime nor composite. It is just 1. Now you might be thinking, it seems to fit the definition of prime. 1 times 1 is 1. That's it, 1 in itself. Not really. It doesn't really fit the definition of prime because technically the definition of prime says numbers greater than 1. And it doesn't really count because it's 1 times 1, which is 1 times itself. So anyway, all that is to tell you that don't consider 1 as either prime or composite. Okay, so we're just going to I'm just going to put an X through 1 because we're using the list to show that Brian's claim is false. So how about 3? Only factors are 1 in itself, right? So that is prime. Okay. Now how about 5? Yeah, only factors are 1 in itself again, so it is prime. Gosh, Brian might be onto something, huh? Look at 7. 1 times 7, that's it. That's all you get. Show's over. So that is prime. Ah, but here where Brian's little claim falls apart. 9, ooh, we could do 3 times 3, right? That's one of our perfect squares. So 3 times 3 is 9. So 9 is composite. 11, prime again, right? We had seen this earlier. 13, 1 times 13, and that's it. It's a primo prime. Ah, but 15, Brian, are you paying attention, Brian? 3 times 5 is 15, so 15 is composite, yes. Now 17 and 19, I believe we encountered earlier, but yes, they are both prime. They are Optimus prime. But even just this little list up to 20 proves Brian's claim false. He says only even numbers are composite. Here we are looking at this list, and 2 of these odd numbers are composite. So in our list, of odd numbers up to 20, two, and we'll put them in parentheses here, 9, 15 are composite. So, therefore, what have we proven? He said only even numbers are composite. So Brian is wrong. Just like saying that, rub it in his face. Brian is wrong. No, just kidding. We're doing it in a friendly way. But he's wrong. And Brian is wrong. And odd numbers can be composite. In fact, this kind of proves it in the inverse. But so Brian's onto something that even numbers will have 1 in itself and 2 as a factor. So almost all even numbers, in all the numbers you can imagine, will be composite. 4, 6, 8, 10, 12. As I say them, you're like, oh yeah, 12 is 2 times 6 and 3 times 4 as well, is 1 times 12. But there's an exception there even. You can't even say, it would be wrong to say that all even numbers are composite. That's right, because of 2 itself. 2 is an even number and can be classified as prime or composite, but its only factors are 1 in itself. So 2 is actually, when you're going numerically through the numbers, counting from least to greatest, 2 is the first prime number. 2 is prime. So we can't even say that all even numbers are composite. I could add that there, but it's overkill. All right, so let's go on to our last little example here, number 4. Well, in number 4, we will do as we often do here in Eureka Land and take what we've learned and apply it to something of a real-life situation. For we have encountered our new friend, Julie, that little grape counter. So Julie counts up her grapes. She's not playing, y'all. Must be good grapes, some scuppernogs or something. Julie has 27 grapes to divide evenly among 3 friends. She thinks there will be no leftovers. Okay, so we're talking about division. We call that, right, remainder. Okay, so no remainder when she divides them among 3. Use what you know about factor pairs to explain whether or not Julie is correct. Well, let's take a look here. So we know 27 is, well, first and foremost, right, 1 times 27. Always start there. And we did this earlier, so you perhaps recall, or can figure out now, that what else can we multiply to get 27? What other factors of 27? What's another factor pair? Yes, 3 times 9. Okay, so that means that 3 can divide evenly into 27, or if you have 27 grapes and hand them out to 3 people, they will get 9 each with no leftovers. So yes, indeed, Julie is correct. But we want to explain it using what we know about factor pairs. I don't want to just say each person will get 9 grapes. While that's true, that's not using what we know about factor pairs to explain what. Okay, so since 3 is a factor of 27, 27 is, and here's some important math vocabulary, evenly divisible. And you'll learn about divisibility rules someday. So it's evenly divisible by 3. That means when we're dealing with whole numbers, it'll divide into it evenly with no remainder. So 27 is evenly divisible by 3, and what does that tell us if it's evenly divisible? And there will be blood. No, that's horrible. Don't say that. There will be no remainder. There will be no remainder. And you notice, see, so this is a case where like the answer isn't what you're going for. It's like, well, do you understand what you're doing? 27 is evenly divisible by 3, so there's no remainder. Well, look, you've done it again. Completed another homework time. So I will see you next time. It is once again homework time.